I'm currently at the site of the Oso Landslide, which you can see right behind me, and occurred on March 22nd, 2014. The slide led to the loss of about 40 homes and other structures, including the burial of State Route 530, which is now renamed the Oso Memorial Landslide Highway. 43 people died in this slide, which, as you can see, basically took out the entire community that once stood here. When debris swept this entire valley, a half-mile wide valley, all the way to the Stillaguamish River, filling up and damming the river actually when this happened. So the slide traveled 40 miles an hour, which is crazy, filling this entire valley in about 60 seconds and moving 19 million tons of sand, which is pretty incredible. The primary cause of a landslide is the influence on gravity acting on weakened materials that make up a sloping area of land. Because this slide represents such a traumatic event, it's important to consider the factors that led to this landslide. Following the slide, the USGS conducted many different studies that indicate that both geological and hydrological conditions played a crucial role in the induction of this massive flow. Let's consider some variables that are crucial in order to determine a slope's susceptibility to failure. First and foremost, it is important to consider the shear strength, which is the ability of material to resist shear stress, and can be determined by measuring the cohesion of the material, the effective normal stress, which is dependent on the pore fluid pressure, and the angle of internal friction. The equation, known as the Coulomb equation, suggests as follows. An increase in effective normal stress, implying a decrease in pore fluid pressure and decrease in slope angle, as well as an increase in cohesion and an increase in the internal friction, will lead to an overall increase in shear strength. On the other hand, the Coulomb equation suggests that shear strength decreases when effective normal stress decreases, caused by an increase in pore fluid pressure and slope angle. Additionally, this may be caused by a decrease in cohesion and angle of internal friction. The shear stress, on the other hand, is the force exerted by erosional processes directed downslope and causing the mass of rock or soil to shear over the underlying material. This may be determined by the sediment density, gravity, angle and the depth of sediment perpendicular to the slope. According to the force balance first principle, when the shear force is less than or equal to the normal force, there is no movement into the system. Whereas when the shear force is greater than the normal force, movement is induced within the system. Since the shear strength accounts for the normal force in the case of mass failure events, when the shear stress exceeds the shear strength, the slope will be prone to failure and will have a factor of safety greater than 1. Therefore, a slope is especially prone to failure when shear strength decreases. So what's happening with the Oso landslide? Let's go find out. First, it's important to consider the geologic context of the slide. We are currently looking up, right up there, at the southeastern edge of Whitman Bench, a land terrace about 800 feet above the valley floor and consisting of gravel and sand deposited during the most recent glaciation. Now, I've picked up some of this sediment here so we can take a closer look, and as you can see, it's mostly this sandy, pebbly sediment, and there are actually some rocks in here that are pretty big. So the grain size is very varied, and it's indicative of a glacial till. When the Puget Lobe of the Cordilleran ice sheet moved south from British Columbia, filling the Puget lowland, various mountain valleys were dammed and lakes were formed. Sediment washing down from higher mountains settled in these lakes, forming a layer of clay. As the glacial ice pressed higher against the western end of Mount Fairley, water flowing around the edge of the ice from the north was forced around the mountain, eventually pouring through the long valley extending to the northwest and carrying with it the sand and gravel, which entered the glacial lake and dropped out to form a delta, the remnants of which is now Whitman Bench. So when glacial retreat followed, it left behind this former delta hanging over the current valley floor. So what do we have left here today? Well, it's basically what I just showed you. The slope that has failed is largely made up of loose sandy soil underlain by a compact layer of sand and silt that originally made up that glacial lake, the floor of that glacial lake. So that blocks the flow of water and allows water to accumulate after it seeps through that layer of glacial till at the interface between the glacial till and the more dense clay. Thus, water infiltrating from the surface flowed through the surface and accumulated in a form to form stability weakness in that zone.
If we look back at our Coulomb equation, the low cohesion of this material is especially important.
If we consider the hydrology of the region, we know that this region has heavy seasonal precipitation. While the slide may have occurred on a dry and sunny day like today, it followed a period of unusually high precipitation in the area. This would have given rise to high groundwater pressures. In fact, analysis from a nearby weather station showed that the 45 days preceding the slide had been wetter than 98.2% of the 45-day periods in an 86-year record. Now, looking at our Coulomb equation again, we are not only talking about a low cohesion of material, but an increase in pore fluid pressure, leading to a decrease in the effective normal stress. Both will result in a lowering of the shear strength resisting the shear stress, which is only increasing as the sediment becomes denser over geologic time due to sediment dilation during prior episodes of landsliding at the site, including the first stage of the slide on March 22nd, and long-term relaxation of glacially unloaded fine-grained sediments at the base of the landslide. Simulations of the landslide indicate that basal liquefaction and high landslide mobility develop only if wet sediment meets one condition. M0 must be less than M critical, where M0 is the initial solid volume fraction and M critical is the static critical state volume fraction. In the case of Oso, sediment underwent pore space contraction during the early stages of landslide motion. The landsliding of wet, loosely packed sediment that contracts as it fills can be accompanied by abrupt increases in basal pre-water pressure, speeding up the development of high pore water pressures throughout and making the material highly mobile. Thus, only an M0 slightly smaller than M critical is required in order for the pore space to decline, causing an increase in pore water pressure and a decrease in friction strong enough to induce liquefaction and rapid acceleration of the slope. As we look at the site of the Oso landslide today, this provides us with a warning for the future. We must carefully examine the factors which play a role in determining the susceptibility of slope failure, including As we look at the site of the Oso landslide today, this provides us with a warning for the future. We must carefully examine the factors which play a role in determining the susceptibility of slope failure, including the geologic setting and the composition of soil as a result, as well as the climatic forces which contribute to weakening slopes such as these. Thank you.